So in this video, I will solve some exam type problems. So probably we will solve up to 3 to 4 problems. So all this problem will become the part of tutorial 1. And how these problems are designed. So mostly these problems are directly related to distillation. So obviously you're not going to design the distillation column itself, but we are trying to predict some of the fluid properties that we need to design the distillation column. So this is what you are going to do by solving the next 3 to 4 problems. And some of the take-home message from this tutorial is to how to get or how to use the vapor pressure of the pure components. Yeah. So what we are going to do is we will get the vapor pressure of the pure component, and from that, using that information, so we are going to deal with systems that involves multiple components, and then we are going to calculate some of the multiple components, and also that involves two different phases, for example liquid and vapor. And then we will calculate something called as a total pressure, and then some easy stuffs like a molar percentage and of the components in the liquid and on the vapor side. So I will, once we explain the problem, once we solve the problem, we will know what I talk about. And then each of these problem are designed in a way so that you can, if you know how to read the problem, and if you know to how to make sense out of the problem, then you will need only 10 minutes or maybe even less than that to solve all of these problems. And obviously to solve some of the problems that we will discuss in this tutorial, obviously you need to know some gas laws. So even if you don't know, I will quickly explain them, or maybe I will give the formulas at least, so that you need to solve these problems. They're very simple and easy to remember, so these are, if you apply common sense, then you can easily remember this gas laws. It's very straightforward equations, huh? No big derivations involved, no big mathematics involved, obviously. And then for the moment, we assume all these gas laws work, and then I'm going to assume that you already know all the gas laws. If not, I'll quickly revise them, so you don't have to worry. So let's solve the first problem. First, I will read the problem. Only then, um, if you read the problem, you almost solve the problem, at least the first 20% of the problem. So all you need to know is read the problem carefully and try to make sense out of that, and take a note of the parameters given. So what's the problem is, so we have a solution that contains 50% benzene and 30% toluene and 20% xylene. So clearly, it's what it says is we have some, just let's call this some vessel. You have some liquid, so that has a 50 percentage of benzene, that 50 percentage of benzene, and then 30 percentage of toluene and 20 percentage of solution xylene, all by weight. So they are weight percentage. Yeah? So take care of the units, and this solution is maintained at say 100 degrees centigrade. So if it is at a temperature of 100 degrees centigrade, then we can expect some partial vaporization. So which means at 100, when T is equal to 100 degrees centigrade, this solution should have partially vaporized, and then it should exert some pressure on the top portion. Yeah? So you have different molecules here. So these molecules will contain benzene, toluene, and also xylene. So what, and the temperature and the whole system is maintained at 100 degree centigrade. So what we need to do is, so obviously this, if you put a pressure probe, it will read something called P, that's, or PT maybe. PT means total pressure. So this total pressure is contributed by three different molecules, benzene, toluene, and xylene. So this should be sum of all these three gas pressure exerted by three of these components. So let it be like say PA, PB plus PC. Yeah? So these are small p's, yeah, so not capital P's. So all they need to they calculate that is, sorry, the question says we need to calculate the total pressure, and then um, and another thing is we have to calculate is the molar percentage composition. So what's the molar percentage of benzene, toluene, xylene in the gas or in the, I mean in the vapor, and also what's the percentage composition of benzene, toluene, and xylene in the liquid phase. And we have some details here. So we have the vapor pressure and the molecular weight. So molecular weights is something that we need to convert weight to mole percentage. Yeah? So if you have something weight, you divide by molecular weight, that should give the mole percent. Something it should convert the quantity into molar units. This is a basic rule you should have studied in the mass balance, heat, energy and mass balance module. So, and then you will also learn from this exercise that how to use the vapor pressure of the pure component. So what do you mean by the vapor pressure of the pure component? So vapor pressure of the pure component is something like that you can get from the lab through experiments. Imagine you start with a solution of benzene. Let's maintain this solution temperature at T, where everything will be in liquid state. At some temperature, say 100 degrees centigrade. So if you maintain this whole system at 100, then this solution will partially vaporize and then it will exert, it will move to the gas side, yeah, or the vapor side. And if you put a pressure here, it will exhibit some pressure. We can call this pressure as vapor pressure. And we have this value for all the three components at 100 degrees centigrade. So which means we have to do three different experiments with just pure toluene, pure xylene, and then we get the vapor pressure, which is given here. So vapor pressure at 100 degrees centigrade is given here for benzene, for toluene, and xylene, and obviously we have their molecular weight. So these are some information which is already given in the problem. And then I also have some gas laws written here. So what is this? It's called Raoult's law that tells something about this vapor pressure of the pure system. And then so I added the notation here. So pi is the vapor pressure of the pure component. So take a note, this is for pure system. If it's for component I, it's the vapor pressure of component I multiplied by, so if we have a mixture, in this case we have three components. So in this case, so let's say we have a total pressure, and let's say this pressure is contributed by three different molecules, and also we have some liquid that contains three different components. If we know the mole fraction of component I, and if we know the vapor pressure of that component I, then we can calculate the partial pressure of that component here. Yeah? So what is this PT? So PT is the sum of all the partial pressures, am I right? So sum of PI, so this is small p, so this should be equal to PA small p suffix B plus small p suffix C. So if we have, so we know that PT is the sum of all these three. So how to get this partial pressure PB, PC? This is something that we can get using the Raoult's law. So Raoult's law applies if the solution or the system is said to be in ideal conditions, yeah? Or an ideal solution. So this should be okay for the moment. So and this is something, okay, this is a simple expression. This is something we call it as a Dalton's law. Dalton's law, and this is the another version of the Dalton's law. So what is this? The mole fraction of the component I. So if we have three components in the vapor side at particular temperature T, in this case 100 degrees centigrade. So if we know P small pa, comma partial pressure of B, partial pressure of C, and if we know the total pressure PT, so then the ratio of each of these components, I mean ratio of the partial pressure of each of these component divided by PT, so that should give something about the mole fraction of each component in the vapor phase. So that will be small pa by pt. So this should be equal to mole fraction of component A, small p by pt. This should be equal to mole fraction of component B, and then small pc divided by pt. This should be equal to mole fraction of component C. And for ith component, small pi by pt, that should be equal to y of I. That's the mole fraction of the ith component. So that's the form of another form of the Dalton's law. So we have all the necessary formulas to calculate. So if you go back to the question, what we need to calculate is the total pressure. So what's the total pressure? And then the molar percentage composition of the liquid and the vapor. So let's calculate that one by one. So for the moment, we can assume that we have roughly 100 kilograms of solution. So I'm going to set a base is 100 kilogram of solution. It, if you want, you can keep it to 1 kilogram, but for my convenience, I'm going to consider that we have a system that has 100 kilogram of solution, and let's heat it to 100 degrees centigrade so that we will know what's the vapor pressure of each of those components for the case of pure system. Yeah? So, okay, let's try to solve the problem instead of talking too much. So what we have here, we have 100 kilogram of solution. So let's write the components involved. So what are the components involved? So we have the silane. So we have three components, and then we also know the amount. Let's say the mass, or maybe mass in kilograms. So if we go back to the problem, we have some weight fraction there. So what's that? 50% benzene, 30% toluene, and 20% xylene. So which mean if you convert them into kilograms, it will be exactly 50 kg, 30 kg, and 20 kg. So if you take the total, that will be equal to 100. And if you take the weight fraction, this should be equal to 50%, and this should be equal to 20% in terms of weight fraction. Yeah? So that's how you calculate. And then I'm going to convert them into molar units. So molar units, so before that, let's write the molecular weight, because this is something already given in the problem. So molecular weight of benzene is 78, toluene is 92, and xylene is 106. So from there, we can obviously calculate the mole in molar. We can convert the weight to the number of moles. So how do you convert it? So it's weight by molecular weight. So 50 by 78, 30 by 92, 20 by 106. So you should get some numbers here. So 0.641, I already calculated this. 0.326, this should be equal to 0.189. If you take all the sum, that should be equal to 1. Yeah? So the total mole fraction should always add up to 1. Yeah? So, so from here, we can also convert everything into mole percentage. So mole percentage is what is, oh sorry, this is not correct. This shouldn't add up to 1. So this is, we just convert it into mole. So if you take the sum, this should be equal to 1.156. Sorry, it's my mistake. And then mole percentage, this is something we can calculate, 0.641. So that's why it's better to sit in home and solve the problem. Yeah, even if you think you are an expert, still you will do a mistake. So it's always better to practice. And this whole multiplied by 100, and similarly here you get 0.189 multiplied by 100 divided by 1.156. So this should be equal to 55.45, and this should be equal to 28.20, and this should be equal to 16.35. Only if you sum all this one, this should total to 100. Yeah? So this is in mole percentage. Yeah, these are really basic things you must have done already in mass and energy balance module. So let's go back to the question again. So where we are now. So now we have to calculate the total pressure. Yeah. So total pressure, to calculate total pressure. So if you remember from the Dalton's law, to calculate total pressure, we need partial pressure. Yeah. So this is something that we can get from the Raoult's law. So we know that Raoult's law state that, so capital PA, so this is the vapor pressure multiplied by the mole fraction Xi, and then PB multiplied by XB. So this should be XA, sorry, and this is small pc. So this is capital PC. So capital P underscore C, this means, oh, sorry, this is small pc. Yes, this is partial pressure of C. So this should be equal to um, capital P underscore C multiplied by X multiplied by C. So capital P underscore I, so this is nothing but vapor pressure. So that means this is vapor pressure of A, vapor pressure of B, vapor pressure of C, and X suffix A, this is mole fraction of A, X suffix B, mole fraction of B, and X suffix C, mole fraction of C. Yeah. And this value, mole fraction, this is something that we already calculated now for the, so if you go back to the, so we started with the 100 kilograms of solution, and from there we calculated the mole percentage here. Yeah. So let me change the color so I can show you. So you have here some numbers here. 55.45, that's a mole percentage of benzene, and then 28.20, that's a mole percentage of toluene, and 16.35, that's a mole percentage of xylene. You know, from there we can get the, so that's, we have the mole fraction of each of these components. So we already have the vapor pressure from the table. So if you go back to the question again, so we have the vapor pressure in the table, so just multiply it. So PT, so that should be equal to, vapor pressure is 1340. So this is sorry, this this is for benzene. Yes? Partial vapor pressure of benzene multiplied by mole fraction is 0.5545. Yeah? So 55.45 is mole percentage. So I convert it into mole fraction. So this is for benzene, or this is the partial pressure of benzene, plus 560, that's the vapor pressure of toluene, multiplied by partial pressure of toluene, which, sorry, mole fraction of toluene is 0.2820, plus vapor pressure of xylene, so we know that that's 210. This is from the table, multiplied by the mole fraction of xylene in the solution, so that's 0.1635. Yeah. And note that we are using pressure in, we are expressing pressure in terms of millimeters of mercury, so which means your PT should be in millimeters of mercury. Obviously mole fraction has no units, so if you sum all these values, so this should be equal to, I already did calculated these values, but you can cross check it if sometime I might have did some mistake. Total is, so this is the partial pressure of benzene 743. This is the partial pressure of toluene. This is the partial pressure of xylene. So if you sum all the three, then according to Dalton's law, that should give the total pressure. So 935.2 millimeters of mercury. So I think we solved one section of the problem. So now we also need to calculate. So if you read the question, I also ask you to calculate what the composition. Where is that? The molar percentage composition of the liquid and vapor. So liquid we already calculated. Vapor we have to calculate. So if you remember the Dalton's law, so other version, I said to you mole fraction of component I, that's equal to partial pressure of component I divided by the total pressure. Yeah? So therefore for benzene, this should be equal to partial pressure of the benzene, and that is here, yeah, 743 divided by the total pressure, which is 935.2. So this should be equal to 0.7945. Obviously, I ask you to express in terms of mole percentage. So this should be 79.45 percentage. And then y xylene, same rules. We know the partial pressure of xylene by total pressure. This should be equal to 0.1688, 16.8 percentage. Okay, so we can do this for xylene. So 34.3, 935.2. So that should be equal to 0.0367. This should be equal to 3.67 percentage. Yeah, so that's all. So this is problem one. So what we learned from this problem one is obviously we should learn how to read the problem. That's the first thing. And you should know what are the things that are given. So what we have is we have solution that's maintained at some temperature, and it's a three component system. So you have three different components, and they exert some total pressure contributed by three of those individual components. So on the liquid side, you will have mole fraction of all these three components, xi in general, and then you also have on the vapor side, you have partial pressure exerted by three components, p suffix I. So, and then we also know how to apply Dalton's law, and then we also learned how to use Raoult's law, yeah, Raoult's law to get the partial pressure. Yeah? So for partial pressure of each of the component in the vapor phase. For that, we learned how to use the Raoult's law that have some information about the mole fraction of those components in the liquid side, and then it also have some information about the vapor pressure at that particular temperature. Yeah, so that's all for this problem. And we also learned how to get this one, the mole fraction of the components in the vapor phase, provided we know the total pressure, provided we know the partial pressure of the each components on the vapor side. So this should be enough. Let's go to the next problem. So in this video, we will solve another problem. This problem, I can call it like something which is directly related to or relevant to distillation. Yeah. So obviously we are not going to design the distillation column, but we are going to get to something really important, the record fluid properties. So something called as XY diagram or TXY diagram. So this is something you absolutely need in order to design distillation column, and you should also gain some understandings about the so-called XY diagram. And if you remember in the problem one, what we learned is something interesting. So what we learned in the problem one is how to apply some of the gas laws. Yeah, so if you know how to get the partial pressure, sorry, if you have the partial pressure of each component, so just follow the pen. It's in the red color now. So if you have something on the vapor phase that contains more than one component, so if you know the partial pressure, then we can get the total pressure from the so-called Dalton's law. And then if we also know the partial pressure and if we know the total pressure, then we can calculate the mole fraction of each component in the vapor phase. So this is what we learned in the first example. And then another thing that we learned is something how to use the so-called Raoult's law. So if you have, so Raoult's law is something that requires vapor pressure. So if you have the vapor pressure, and then if you know the mole fraction of each of those components in the liquid side, then it allows you to calculate what's happening on the pressure exerted by each of those components on the vapor phase. So really very cool and interesting law. Yeah? So that allows you to calculate, that tells something about the vapor phase based on the information available in the liquid phase. And obviously you also need the very important parameter, the so-called vapor pressure of the pure system. So if you know the vapor pressure of the pure system, then it allows you to calculate the pi of the components of the fluid that contains more than one component. Yeah, so that's what we learned, and then we are going to extend the knowledge that we gained uh, in the previous problem, and then we are going to slightly do some not advanced calculation, maybe few more steps that allows you to calculate the TXY diagram, or something we call it as the vapor liquid equilibrium data, VLE data. So what's that mean? It's like if you have some system, let's say you have liquid, you have vapor, and say this is maintained at some particular pressure, and how the composition changes in the liquid and in the vapor side. Yeah, how the in the case of say this fluid mixture contain two components, say A plus B. So as you change the temperature, how the percentage composition of A and B changes in the liquid side and also in the vapor side. So, and then we are going to define some notations. X is something refers to the mole fraction of the more volatile component in the liquid side, and Y is the mole fraction of the more volatile component in the vapor side. So these are some notations. So I can write it here. So it's the mole fraction of the more volatile component on the liquid side. And similarly, Y refers to the mole fraction of the more volatile component on the vapor side. So these are some notations that we are going to define. Then what we have here. So let me read the problem. So that should give you some idea. So what we have here, we have a solution of methanol and ethanol. So clearly it's a two component system. So what this let's call this, if this is a system, let's call A and B. So let A be methanol and B ethanol. Yeah, and assume that they are substantially ideal, so which means you can use the Raoult's law to predict the fluid properties. Uh, and it also means we can also use some of the gas laws. This gas laws applies. So if we, whenever we are implementing this type of equations, which mean we have to assume the system is ideal or the system is supposed to be ideal. So that's the idea behind the so-called ideal systems. And then what we have here is we are supposed to compute the vapor liquid equilibrium data. So I will tell you what's that. Vapor liquid equilibrium data is just a plot of x, y, or x versus y, or temperature versus x and y. Yeah? And then we also need to calculate the relative volatilities and determine an average value of relative volatilities. This is something we didn't cover in the lecture, but it's very easy to define here. Yeah. So when we are solving the problem, we can also learn how to define the so-called relative volatility and how to get these values, an average value, over a range of temperature. And then what we have here is the vapor pressure. This is something you should already know. It's called Antoine expression. And what this expression relates is something vapor pressure with respect to the temperature. So this is for a pure system. So how this must have obtained in the lab, obviously they use a lot of sophisticated equipments, but all we have here is we have some pure methanol, and then you heat it, say, to temperature, some particular T, and then you check what's the vapor. So it creates some vapor on the top. So what's the pressure, corresponding pressure? So that's nothing but vapor pressure. You raise the temperature and record the new vapor pressure, increase the temperature, record the new vapor pressure, and then you finally correlate temperature. So you will have a lot of data, T1, T2, T3, P1, P2, P3. Then you, and this, the relationship between these quantities follow this particular expression, Antoine expression, and these are the constants involved in the Antoine expression. So, and this is nothing but your temperature. So temperature versus vapor pressure of the pure methanol, and we have the temperature versus the vapor pressure of the pure ethanol, and using we have some relationship connecting these two parameters, and so this is nothing but Antoine expression. And then I have some I explained what's what. So these constants are nothing but Antoine constants. And then I just ask you to trust the gas laws and assume they are ideal system, or and then which mean these laws apply Dalton's law and then the Raoult's law. This rule apply to solve this particular problem. So what's this compute the vapor liquid equilibrium data means? So vapor liquid equilibrium data I already mentioned what's that, and what's this TXY diagram or XY diagram? XY diagram is just a plot of X versus Y. So this is the mole fraction of the more volatile component in the liquid phase, typically ranges from 0 to 1 because it's a mole fraction, and then the mole fraction of the more volatile component in the vapor phase should range from 0 to 1. We will have a diagonal line, and typically you may see something like that. If one component is more volatile than the other component, and if the system is ideal, then you will see some curve, something like that. Yeah. And then similarly, what I ask you to plot is another one, t versus x comma y. So if you plot a t versus x, you may get some graph like that. If you plot t versus y, you may get some graph like that. Yeah. And obviously this range from 0 to 1. So this is what we are going to, we are supposed to get these two, the data required to plot these two graphs. These are nothing but vapor liquid equilibrium curves. So we will try to calculate one by one with the very minimum information that we have at the moment. So what are the information that we have at the moment? The pressure is set to 1 bar. Yeah, so what 1 bar? Yeah, so what does that mean? You have a system, you have some liquid, let's say you have some temperature, you have some vapor phase, and this vapor phase pressure, total pressure, is equal to 1 bar. And what I ask to do is, so let the pressure be fixed, but if we change the temperature alone, so if you keep on increasing the temperature, how the composition of the two components vary on the vapor side and on the liquid side. So let's use the notation. So methanol, I'm going to call it component A, and ethanol, I'm going to call this as component B. And then the mole fraction of component A in the liquid side I'm going to call XA, and the mole fraction of the component B on the liquid side I'm going to call XB. And similarly, the mole fraction of a component B on the vapor side I'm going to call YA, and the mole fraction of component B on the vapor side I'm going to call it as YB. So these are some notations that we are going to use. So at the end we are going to plot XA versus YA, and here T XA comma YA. So these are nothing but, okay, you don't have, no need to be A, so we are going to plot the more volatile component here, and then X and Y of the more volatile component. Still we don't know which is the more volatile component. That's your job to identify, by solving this problem. So it's very easy to, it's not a, it's not a rocket science. It's very easy. I will show you how to do it. So you already have vapor pressure and you have a temperature, and then if you expect this type of problem in the final exam, I may give some additional note. So this is to save your time, and so this note may look, how it will look like. It may look something like uh, how I can give that note. I can say that okay, predict the vapor, compute the vapor liquid equilibrium between the temperatures. So I can write it. So compute the vapor liquid equilibrium uh, uh, or maybe at the temperatures that range from, so this is something I can add if you get this type of problem, that range from what to what, maybe 64.75 degrees centigrade to 78.33 degree centigrade. I will tell you why these numbers are here. It will make sense once we solve the problem. But for the moment, just believe that I may give this type of note if you have this type of problem in the final exam. Yeah, so let's do this one by one. So what we need to do, what I ask you to calculate is the, so if you have the system, something like that. So I put the P should read 1 bar, and then T should range from 64.75 to 78.33, and within this range, what's the XA and what's the YA here? Yeah? And we can, if we have XA, we can calculate XB obviously. If we have YA, we can calculate YB obviously. And what information we have? We have is the vapor pressure of PA, vapor pressure of uh, sorry, vapor pressure of component A, and vapor pressure of component B. Yeah, so this means okay, we don't have it, but we have a relation to calculate PA and PB. This is something we can get from the Antoine expression. Yeah. So once we have this one, then we can apply the series of gas laws, Raoult's law, Dalton's law, to get XA and YA. So so what's maybe I can write the formula straight away. So we know that PT is partial pressure of A plus partial pressure of B. So this should be the components here on the top of the system vapor phase. So this should be equal to 1 bar. So this is something I gave in the problem. And then to calculate PA, so we know that Raoult's law applies. So PA can be calculated using the Raoult's law, which is PA, capital PA multiplied by X of A plus capital PB multiplied by X of B. Yeah, so so what's this? So this is the vapor pressure of A. This is the vapor pressure of B at the different at particular temperature. Yeah, and then this is the mole fraction of A, something that we have to calculate. This is the mole fraction of B. This is something that can be calculated. And PT, this is which is equal to 1 bar. So PA and PB can be obtained from Antoine expression. XB can be replaced. How to replace? So if you go back to this one, this same box, let me change the color to blue. So you have two components, yeah. So A plus B, so which mean XA is the mole fraction of A, XB is the mole fraction of B. So this total should be equal to 1, yeah. So XA plus XB, that should be equal to 1. So XA is equal to 1 minus XB. So you can plug this value here. So that makes this expression PT is equal to PA, capital PA, that which means vapor pressure multiplied by XA plus capital PB, which means vapor pressure of component B, into 1 minus XA. So this is equal to 1 bar. So if we know PA, if we know capital P suffix B, this is vapor pressure of B, then we can calculate XA, yeah, because we know the total pressure is equal to 1 bar. And all we need to do is we have to get PA and PB at different temperatures. Yeah, so that should allow you to calculate XA at different temperature. And then once we have XA, so we can calculate obviously the partial pressure using the Raoult's law. So once you have XA, we can get the partial pressure of A. This is equal to X of A. Yeah, yeah. And then what? So this should be equal to uh, x of A multiplied by P of A. So this is nothing but the partial pressure. And then to get Y of A, that should be equal to partial pressure of A divided by the total pressure. Um, so this is equal to 1 bar. This is something already given. So this should allow you to calculate Y of A at different temperature. So everything begins by estimating the vapor pressure at different temperature. From there we get XA. From XA we get YA. Yeah, so let's do that. So let's try to solve the problem. So I already said how to obtain some of this value. So let's begin with let's try to calculate T value. So not to calculate. So let's create another table. Let's say temperature. Let's begin with temperature. Okay, let's begin with temperature. What we have here. So all we need to calculate is for the range of temperatures, say ranging from 64.75 to 78.33. We are supposed to calculate the mole fraction of uh, the more volatile component, and then the in the liquid phase, and the mole fraction of the more volatile component in the vapor phase. So until I just assume that this is going to be the more volatile component, but we are not sure. But this is something we can prove it or test it mathematically. So 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 how to do that? How to test it mathematically is or check mathematically is something we have to go back again. Yeah, so I'm going to talk about this particular value 760 and 760 here. Yeah? So if we take the PA, which is the vapor pressure of the component A, the pressure is equal to 760 when the temperature is at 64.75, whereas for the case of PB, the pressure is equal to 760 when the temperature is at 78.33. So imagine if you have a pure system, just to say we have component A. So if we heat this component at to 64.75, this is going to exert a pressure of 760 millimeters of mercury. Yeah? If you take a system that contains only component B, you have to raise this particular solution to temperature of 78.33, which is here in the table, in order to get the same vapor pressure of 760 millimeters per millimeters of mercury. So which means that component A exhibits more vapor pressure at this particular temperature. So obviously this means component A is the more volatile component. Yeah? So it exerts more vapor pressure when you compare to component B at the temperatures considered here. So that give you some idea which is the more volatile component. So you have to, if asked in the exam, so which one is the more volatile component and why? So you have to explain all this points which I mentioned to you now. Yeah? So you can compare, say, at the particular temperature T is equal to 64.75, or maybe over the temperature ranging from 64.75 to 78.33. The vapor pressure of component A is more than the vapor pressure of component B, which obviously indicates that so component A is the more volatile component when you compare to component B. Yeah? So this is something for your thought process. So let's go back to the problem. So we have to calculate XA and YA. So how to do that? So I already gave you the formula. So we have PT. So this is nothing but our total pressure, which is equal to partial pressure of A and partial pressure of B. This is something which is equal to vapor pressure of A multiplied by XA plus the vapor pressure of B multiplied by 1 minus XA, and this is equal to 1 bar. This is already given in the problem. So say for example at 64.75, if we go back to the table above, we already calculated. So at 64.75, the vapor pressure of PA is 760 millimeters of mercury, and at 64.75, the vapor pressure of component B is 433. Yeah, so let's substitute those values here. So 1, this is not, or if you want, we can express in millimeters of mercury. So instead of 1, we express in millimeters of mercury. So this is 1 bar. Yeah? This is what given in the problems. I'm going to express in terms of millimeters of mercury. So this should be equal to the vapor pressure at this particular temperature, which is 64.75, is 760 multiplied by XA. This is something we have to calculate. Plus PB is 433 multiplied by 1 minus XA. If we solve for XA, we will get a value of 1.0. Yeah, and then what else we can calculate? Yeah? So if XA is 1.0, so what does that mean? So if P is reading 1 bar, and if XA is equal to 1.0, which means XB should be equal to 1 minus 1. So because XA plus XB, that's equal to 1. So XB should be equal to 0, which means no component B in the vapor or liquid at this particular temperature. Yeah, so xb, and let's calculate for ya. Similarly, let's calculate for ya. So if we have xa, then from the Raoult's law we can calculate pa is equal to partial pressure of a is equal to xa multiplied by the partial pressure of a at that temperature. So this is 1 multiplied by 760. So partial pressure of a is equal to 760 millimeters of mercury, and so which means the mole fraction of a at 64.75, that should be equal to partial pressure of a by total pressure, that should be equal to 760 by 760, that should be equal to 1. So which means ya is equal to 1. So this also means so in the vapor fraction, if ya is equal to 1, so and we know ya plus yb, that's equal to 1. So therefore yb is equal to 1. So what it means, so at 64.75 degrees centigrade, xa is equal, sorry, yb is equal to 0, sorry, no? So because this is 1 minus 1, that's equal to 0. So xa is equal to 1, ya is equal to 1, xb equal to 0, yb equal to 0. So what this particularly means is there is no component B in the liquid and the vapor, and everything is just component A. So which mean at 64.75 degrees centigrade, at if the pressure reaches 1 bar, 64.75 degrees centigrade, and at 1 bar, everything will be just a pure component. Yes, it will be just, that should be equal to the, so what does that mean? Um, so let's go back slightly down. So this means, so this should be equal to the boiling point of A. So if you are at the boiling point of a particular component, then at that particular condition, okay, let's go. I don't know how to go down. Um, so what does this mean? And which means, so in a two-phase mixture, if your pressure is P is equal to 760 millimeters of mercury, and all of this pressure is contributed only by PA, which means you just have pure component. Yeah, so it should be equal to the properties of a pure methanol. So we'll come back to this later. So once you have TXY diagram, I can explain you where is the boiling point of methanol and where is the boiling point of ethanol. Okay, let's understanding the TXY diagram or XY data as a function of temperature is not it's not actually easy. You should have really some good understanding of how the liquids behave at different temperature, and you should also have some good understanding about the partial pressure and the total pressure, um, and the relationship between the mole fractions involved. Yeah? So let's first develop the T and XY diagram, and then we worry about how to understand the data. Yeah? So what I have here, so we already calculated XA, and then okay, and we already calculated YA as well. Yeah, so okay, let me change the color. So we already calculated YA, we already calculated XA. So let's enter that value in table here. So should be equal to 1, and this A should be equal to 1. This is something we calculated now. So similarly, we can calculate for 68, we can calculate for 72 and 76. I already calculated these values, so this should be equal to 0.724. Here it should be equal to 0.819. At 72, XA should be equal to 0.415 and YA should be equal to 0.819. Similarly, 76, it should be equal to 0.143. Just check the values whether they are correct or not. If not, send an email to me. Should be equal to 0 and this should be equal to 0. So this is already interesting. If you see here at 64.75, XA and YA are 1 comma 1 and then 78.33 XA and YA are 0 comma 0. So what is this one? XA comma YA. So both corresponds to, if you see here XA and YA 1 comma 1. So which mean so both corresponds to mole fraction of the component A in the liquid phase and vapor phase. If they both are equal to 1, which mean the other component is equal to 0. So this should be a pure system and this temperature should be equal to the boiling point of A. Yeah. And if you come back here at 78.33, so what does this mean? XA and YA, the mole fraction of the more volatile component in the liquid phase and in the vapor phase, they both are 0, but still it exerts a pressure of 1 bar. Yeah. So what it means, it says, which it means at 1 bar, if the solution boils and if it exerts a pressure which is equal to 1 bar at this particular temperature, and which mean that should be the boiling point of the component B. So this particular temperature, this should be the boiling point of the pure component B, as the mole fraction of the more volatile component, or in this case the mole fraction of A and B is equal to 0 at this particular temperature. And here if you see XA comma YA, which is equal to 1 comma 1, and then 1, X is equal to 1, Y is equal to 1, which means there is a 0 contribution from the other component, which is B. So this should be the boiling point of the component A. So that's how we have to understand about the XY data. It's maybe slightly confusing, but that's how the things work. The vapor liquid equilibrium data works, and that's how you interpret them. Yep. So if you plot them, so what I ask you to plot is X A versus Y A. The more volatile component is A, and its mole fraction in the liquid phase versus its mole fraction in the vapor phase. So since it's mole fraction, it should be ranging from 0 to 1, 0 to 1, and there should be a diagonal line. And if one compound is more volatile than the other compound, and if the more volatile compound is A, then you may expect some graph like that. So this is something you have to check for me, and then you have to plot it in the if I ask you to plot XY diagram, you have to plot in the exam and then try to connect these points. And then another thing that you have to do as part of this problem is to plot the so-called TXY diagram. So which is X comma Y. Maybe I can plot. Okay, temperature is on the y-axis, and then let's plot x, express x in blue and then y in green. So if you plot temperature versus x comma temperature versus x, you will get something like this. Then if you plot temperature versus y, you may get some trend that may look like this. Yeah, and this point, this is nothing but 0 comma 0, because you are on the axis is here 0, and this is 1. Since this is expressed in mole fraction x comma y, so this value should range from 0 to 1, and this particular point, this should be equal to 1 comma 1. So this is nothing but the boiling point. This is nothing but the boiling point of the more volatile compound, which is point A, and this particular point where you see 0 comma 0, so this is nothing but the boiling point of the the, the less volatile compound, which is uh, the component B, in this case ethanol. So this value should be equal to 78.33, and this temperature, if you draw some line, so this temperature should be equal to 64.75 degrees centigrade. So that's the boiling point of the methanol, and 78.33, that's the boiling point of the ethanol at temperature. Temperature is very important, at 760 millimeters of mercury. And then another question which I asked is, say something about the relative volatility. We know one compound is more volatile, so which and okay, relative volatility is something that we didn't define during the lecture hours, but I can define now. So this is just the ratio of the vapor pressure of the more volatile compound divided by the vapor pressure of the less volatile compound. So this is something we already calculated, am I right? So if we go back to this, if we go back here in this table, so we already calculated the vapor pressure of A and the vapor pressure of B at different temperatures. So follow the red color ink. So we have here vapor pressure of A, vapor pressure of B. From here we can calculate the alpha value, which is nothing but PA by PB. I already calculated this value, so I can enter them. Later you can check 1.755, 1.727, and this I see already some interesting numbers there, and 1.674, and then 1.661. And if you take an average of these values, if you take the alpha average, so that should be equal to 1.704. And what you see here is the relative volatility doesn't change by a lot with respect to the change in temperature. Yes, it's almost closer to the average value of 1.704. So this is not a bad idea. Okay, this is some take-home message. Is the relative volatility will not change over uh, change by a huge amount with respect to the temperature. Yeah? So and the temperature ranges from the boiling point of the pure component A and the boiling point of the pure component B. So this is something that you should remember. The relative volatility doesn't change significantly with respect to temperature. So alpha A average so does not change significantly with respect to temperature. Why I'm stressing this point is because later when we are going to design distillation column, we are going to make some assumptions that looks like this. I am going to assume the relative volatility won't change by a lot with respect to the temperature. Yeah? So because when you're going to deal with the distillation column, you will have so many stages and each stage will have a different temperature, and we are going to assume that relative volatility in each of the stages does not change by a lot, or they almost remain constant, approximately equal to alpha average. So this is one of the assumptions that we are going to make when we are going to design distillation columns. Yeah. So although we didn't talk about the distillation column or how it looks like, we through this problem we know later we are going to make some assumption which is theoretically okay. Yeah. And that's all for the moment. Okay, here I took a lot of time to solve this problem, but actually in the exam you should be able to, if you practice correctly, you should be able to solve this type of problems maybe in 20 minutes or maybe even less. Yeah, so depending on how good you are in using the calculators. So and then after this we will solve one more problem that will look something similar to this. So that time the next problem I will give the vapor pressure data. So here what we did, if we go back here, I calculated the vapor pressure data from the Antoine equation. uh, instead of that, I'm going to give the vapor pressure data, and then I'm going to ask you to calculate the TXY diagram. So we will solve the next problem. We will try to solve one more problem so that looks something similar to problem 1 and 2. So this problem is really easy one. You have almost all the data that you need to solve this problem. So let me read the problem. So the vapor pressure of the benzene and toluene, so it's a two component system, and it's a two component system. It's benzene and toluene, so one should be the more volatile compound. So this is already given in the table 1, and let's assume the system is ideal, and which means Raoult's law and also the Dalton's law should apply. And then we have to generate the so-called boiling point diagram. So boiling point diagram is nothing but a TXY diagram. So this is something you have to obtain, and the total pressure is given. So PT is 1 atmosphere or 760 millimeters of mercury. So you already have some data here, and then if the PT is equal to 1 atmosphere or 760 millimeters of mercury, then boiling point at that pressure when P is equal to 760 millimeters of mercury. So this is the vapor pressure. So this should correspond to the boiling point of toluene at this temperature. So that's this. And then if you see here, imagine if you're starting with the pure benzene alone, and then if you heat that liquid to 80.1 degrees centigrade, then this pure liquid should exhibit a vapor pressure of 760 millimeters of mercury. So which means 80.1 degrees centigrade. So that's the boiling point of pure benzene. So this should give some idea. Yeah? So vapor pressure of benzene is greater than vapor pressure of toluene at 1 bar. So this means at this particular pressure, PB is the more volatile component, and benzene is the more volatile component, and toluene is the less volatile component. So this is some information there. So we have vapor pressure for the pure system, pure component, and then now we have to predict how X and Y changes with respect to temperature at constant pressure, which is 1 atmosphere. And this contains fluid mixture containing two components, benzene and toluene. So I ask you to identify which is the more volatile component. This is something we already did, and so this is just a note for you. So you may not see this in the final exam if you get some problems similar to this. So if it's a ideal system, then it should obey Dalton's law, and also it should obey the Raoult's law, so-called Raoult's law. So how to solve this problem? So it's actually very easy. So you just use all these equations. So what you have here, let's see PT. So PT is already given. This is equal to 1 atmosphere or 760 millimeters of mercury. So that should be equal to what's this one? PA, small PA plus PB. So this is the partial pressure of A, this is the partial pressure of B, and we know that this PA can be obtained from the Raoult's law, which is given here. So this should be equal to X of A multiplied by partial vapor pressure of A plus PB X of X. This is the mole fraction of this component in liquid multiplied by vapor pressure of the same component PB at that particular temperature. And so what's the temperature here? This is something. So let's begin with 64.75. Yeah. So at 64.75 degrees centigrade. So this will be 1 is equal to, so XA, PA is, if we go slightly go up, so PA is 760. This is the vapor pressure at 80.1 degrees centigrade of benzene plus XB. So we know XB is equal to 1 minus XA. So this should be 1 minus XA multiplied by vapor pressure of toluene at this particular pressure, at this particular temperature. So this is equal to 0. So if you solve this, you will get XA. So okay, sorry, this shouldn't be 1. This is 1 atmosphere. Change this to 760 millimeters of mercury, because we are expressing the pressure in terms of millimeters of mercury. Okay, so let's go down. So if you solve this one, you will get obviously XA is equal to 1. So if XA is equal to 1, then XB should be equal to 1 minus 1, which makes it 0. Now we can calculate YA. So YA is, we know that it's not given by the partial pressure of A divided by the total pressure. So total pressure is 760. Partial pressure of A in this case is 760 as well. So this is at what temperature? 80.1 degrees centigrade. So this is equal to 1. So XA is equal to 1. YA is equal to 1. So which means this is a pure system. And that system contains only component A. So that's why you get X is equal to 1 and YA is equal to 1. Yeah. So in many students, they really struggle to understand this concept. So in a dxy diagram, y you have 1 comma 1 at one particular temperature, and then y you have 0 comma 0 at another particular temperature. So if you find it very difficult to understand, just assume that you are doing some experiment. Begin just with benzene, for example. Then you heat this to its boiling point, 80.1 degrees centigrade. It's going to create some vapor phase, and that's going to read 760 millimeters of mercury. So if you remember, you have only one component. If I'm going to call that as A, and another component in the top, another, so which we again call it as A. So what's this mean? So that component B is automatically 0, am I right? Component B is automatically 0. And if I ask you to calculate the vapor fraction, the mole fraction of component A in this liquid, it obviously is going to be 1, because there is no any other compound. And on the vapor side, the mole fraction of this compound, YA, that's going to be 1. Because you have only one compound, so that's why you get XA is equal to 1 and YA is equal to 1. And similarly, if you take a solution that starts with the toluene, and then if you heat this solution to its boiling point, say which is 110.6 here, so 110.6 degrees centigrade, it should read a vapor pressure of 760 millimeters of mercury. Okay, and let's call this as toluene by symbol B. So if we calculate the mole fraction, XB should be equal to 1, and then similarly on the top, mole fraction of toluene in the vapor phase, YB, that should be equal to 1 as well. So which means XB comma YB, that should be equal to 1 comma 1, or in other words, XA comma YA, that becomes 0 comma 0. Yeah, so that's why if you calculate XA versus YA, so you will get 1 comma 1 at the boiling point, provided the pressure is 1 atmosphere or 760 millimeters of mercury, and then at 110.6 degrees centigrade you will get Xa is equal to 0, Ya equal to 0. So anyway, now I already showed you how to get Xa and Ya. So if you calculate for all the remaining temperatures, you should get the following. So I already calculated, so I'll give the answers now. So but you have to do some model calculations in your home and check whether the results are correct or not. 6. So Xa, this is in mole fraction, so that's why we don't have unit. So this is 1 comma 1, and this should be 0 comma 0. These are the values I already calculated, so I will just fill it for you, and but you have to practice in the home, yeah, because if you think problem is very easy to solve, I don't think so that's the case. You need some at least you have to practice one time. If you do it for two times, then it's even better. So if you study chemical engineering, you have to use a lot of pen and paper, yeah? If not, you will not learn anything. Yeah? So even no matter how smart you are, you have to touch your pen and paper. So that's the only way you can learn the concepts better. So you should get this type of this data. So try to check, do the calculation yourself, and if you get any values that is something different to that of the one given in this table, then you can email me, I can correct it. So all you have to do is, this graph is terrible, you need to plot x comma y and then t. So 80.1 degrees centigrade should be here, and then what is this? Oh sorry, this is not correct. So what's this? 110.6 degrees centigrade, and this should be 80.1. So if you plot x versus y, so this is t versus x. Then if you plot something on the top, versus y, yeah? So that's why it's called a txy diagram. If you want, you can even plot like an xy graph. So x and y, and note that this unit should range from 0 to 1 because both are mole fractions, and here again 0 to 1, 0 to 1, which have a diagonal line. It's really important to draw this diagonal line. So once we are going to design distillation column, that time you will understand how important this diagonal line is. So then if you plot x versus y data, you may get something like that. So that's all for the moment. So what we do, it's good to me until this point. I think that's all the problem as well. So I think probably by week 3 or week 4 we can extend this problem. We can try to design a flash column using the same data. So it's really important that you solve this problem before we go to the next level. So the next level is obviously now we know how to deal with some empirical expressions like Antoine equation, so that relates vapor pressure versus temperature. From there we get Pi at different temperatures. So once we have Pi, obviously we can calculate the mole fraction, the partial pressure of, let's rewrite in the general terms, Pi. So Pi is the partial pressure of component I is equal to the vapor pressure of component I multiplied by x of I. So this is nothing but your Raoult's law. So this equation allows you to get, if you know Pi, vapor pressure, then we can calculate the any other quantities. So if we know xi, then we can get pi. So if we know pi, then we can, so pi is something that you can get from Antoine expression, and xa, once you calculated xa, then we can get p partial pressure of I. So once you have partial pressure of I, then we can get the mole fraction of the component I in the vapor fraction, which is partial pressure of I divided by the total pressure, which is Pt. And then we also learned how to calculate x of I using the gas law. So if we know the Pt, then we can get Pt is nothing but summation of partial pressure of different components, where I is can be A, B, C until say I. So from here we know how to calculate, for example, now PA plus PB partial pressure, and then we can apply the Raoult's law, which is capital PA x of A plus PB 1 minus x of A, that's equal to Pt. From here you get x of A. So you use this x of A to get the P, this value, this the partial pressure of A. Then from there you can get the mole fraction of A in the vapor side. So, and then after this we managed to transpose the data, or translate the data into a txy diagram, where we plotted x and y on the x-axis and t on the y-axis. So from there you get some curve, and we also get something called as the vapor liquid equilibrium curve, typically expressed in terms of x versus y, all in mole fraction. So some diagonal line, and then so that's what we learned so far. And the next one, probably next tutorial, we will see how to, we can label the txy diagram. We can try to label the txy diagram. So we will try to get as many as details as possible from txy diagram, and then we can also do some activity, so that will help to totally exploit the txy diagram. So if you know how to exploit the txy diagram, then you know how to, it's very easy to design a distillation column, or even to understand what's happening in the distillation column. So typically your distillation column will contain some feed, something goes on the top, typically vapor, something comes in the bottom, typically a liquid, and then we are going to heat this liquid and then send this back. So this is a and then take some product out in the bottom, and then the vapor we will condense back. We take some product, and then we will send some of the product in the liquid format back to the column. So vapor will be rising, liquid will be coming down. So there will be constantly some exchange of mass from liquid to vapor and vapor to liquid, and everything will happen in different stages, and each stage will have different temperature. And typically your temperature will say T1, and let's say here T10. So it will come down something like this. So your temperature will be lower in the top, and temperature will be much higher in the bottom. And to understand as such the whole distillation column itself, you need this txy diagram. So x comma y and t. So if you plot something like this, your bottom, the temperature in the bottom is dictated by something around here, and the temperature in the top of your column is dictated by something around here. So this is what you are going to learn. And then you should also know, depending on your feed condition, what temperature you need to heat the liquid in order to create two-phase mixture. So that's the whole idea of generating the txy diagram. So it's not very easy. I was checking some textbooks and some even YouTube videos. Many people fail to explain what exactly happens on in the column. If you have some feed, what's happening on the top, what's happening on the bottom. So there is no clear message connecting what's happening in the top and bottom, and relating it with the TXY diagram. So sorry, but this is something that we can learn, learn through by doing some activity, and that's all for week 1. So next week we will solve a few more important problems. So thanks for listening.